Okay, in chapter 5, we're going to talk about the applications of Newton's laws. So, we developed theories for applying Newton's laws in chapter 4. So, we won't have a whole lot of new theory in this chapter, but we'll just actually have a lot of problems we're solving, a lot of applications. We will introduce a couple things though. So we'll have, we're going to study the conditions that establish equilibrium. So that's when we have Newton's law when the summation of forces is equal to zero. So that's because acceleration is equal to zero. We'll also consider, so we will introduce a little bit of a new thing. We'll have friction here. So we'll introduce friction. So things aren't going to be this idealized frictionless world anymore. And we'll also study elastic forces, like a spring force. So we'll be covering chapters 5.1 through 5.4. So a quick little review from the chapter 4 stuff is we had a couple necessary conditions, or really just one necessary condition for an object in order to settle into equilibrium. And that basically, if it's in equilibrium, we defined equilibrium as not accelerating, right? So we said it's no change in velocity, so we said it was no acceleration. And we know that the thing that causes an acceleration is a force. And force is mass times acceleration. And since mass is never equal to zero, we have to have, the only thing that's equal to zero is the acceleration, and if acceleration is zero, the sum of the forces equals zero, right? So for equilibrium conditions, we say that the sum of all the forces acting on the object equals zero. This is just simply saying mass times acceleration is zero because acceleration is zero. Or we can break it into components and we say that the summation of the forces in the x direction equals zero. So this would mean there's no motion in the x direction. And then summation of forces in the y direction are also equal to zero. So again, there's no motion in the y direction. If we, started talking about three-dimensional things, we could tack on another one here and say the summation of forces in the z direction is equal to zero as well. So that's just basically we're just saying that acceleration is equal to zero. So the same way we considered x and y components of motion separately, when we're doing projectile motion stuff in chapter 3, we considered x and we considered y and we considered them to be independent, right? Well, it's going to be much easier to consider the x and y components of the forces separately as well, just like we saw from chapter 1 stuff and vectors and all that. So since we have all of the concepts that we need for this chapter between chapters 4 and really chapters 1 and maybe a little bit of chapter 3, we have all the concepts we need. So let's go ahead and jump right into an example. So let's say we have here, we're taking this engine out of this car and we're hanging it here so that we can work on it, right? And we have this little setup here where we have, the engine is hanging from a chain. So that chain is in tension, it's being pulled apart. So we'll call that tension 1. And then it's sort of made stationary against the wall by this tension 2. This is what's going to keep kind of this ring here. The tension 1 connects to the ring. Tension 2 will connect to the ring to keep it close to the wall. And tension 3 is obviously going to help to lift it, right, to hold it up. Okay, so this is our setup for how we're going to hold this engine up in the air. And so what I need to know is what is the tension in each one of these chains? And because if there's too much tension, there's too much force, then they're going to break, right? So we'll make some assumptions here. We'll assume that the chains themselves don't weigh anything, which is, in comparison to the engine, is a pretty reasonable assumption. So the first question, and applying Newton's laws, is going to be, what should we free body diagram? That's what we need to figure out. What do I want to draw a free body diagram of? We've done a bunch of them in chapter 4, but now I'm given a problem and I need to find out what should we free body diagram. Well, you think about it, we need to find all of these tensions, right? So actually, if I were just to free body diagram this ring, if I would put a point right here, then I could actually just draw these tensions off as vectors. So I could say there's a vector off in that direction, tension 3. There's a vector off in that direction, tension 2, and a vector off in that direction, tension 1, right? But that's not really that's not really going to get us any answers in the long run. I mean, it's a nice free body diagram. We can draw that one, but we're going to need to know some of these forces. So we might actually need to free body diagram this engine first, in order so that we can find out the tension of one and then translate that tension to the next free body diagram. So since they all act on the ring, it's easiest to free body diagram the ring, but we can't solve it for values unless we have a tension 1. So we need to free body diagram just this engine first. So doing this, here's our picture again here. Here's the engine, tension 1, tension 2, tension 3. It acts 60 degrees. We would say this is 60 degrees off the horizontal, right? So 60 degrees measured off the horizontal, just like that. And 60 degrees, this would be measured counterclockwise off the horizontal, right? Measured in a counterclockwise direction. So first thing here, we have free body diagram of the engine. So, just draw a point here, right? And then we can have, we'll label this. Make sure to label your axes. What is positive, what is negative? Because we'll turn arrows into algebraic signs, plus and minus, after we get done. So there's our positive y, there's our positive x, sticking with standard sign convention here, and then we draw the engine as a dot, and the weight is a vector down, and then tension 1 would be a vector upwards, right? Because we need to think, all right, what do we have to have here in this situation? Physically, what's going on? Is this engine accelerating? No, it's not, right? It's not moving, it's not changing its velocity, it's not changing its position either, right? Both acceleration and velocity are equal to 0. So that means that the sum of forces, and when I draw this free body diagram, the sum of forces have to be equal to 0 as well, which means that the weight must be opposite the tension, right? Equal in magnitude, opposite directions. So that gives us 1. And then I'll draw the free body diagram of the ring right here as well. So then this is another free body diagram of the ring. So the ring now is the dot, and the ring will have some tension 1 pulling down on it, right? Tension 1 pulls down here and pulls up here. It pulls up on the engine, but it pulls down on the ring, right? Tension is always, it's a pulling force, right? That's what tension is. So that's why it's convenient to label these as tension instead of force. So we have tension 1 pulls there, tension 2 is going to pull this direction, tension 3 is going to pull up into the side, right? Well, it's nice to put these counterclockwise off the x-axis here. So this can be, this is 6. If I draw a line here, then that's 60 there. Then this is the opposite interior, so this is 60 degrees as well. Okay, so 60 degrees, tension 3x is that. And then we can go ahead and break apart tension 3 into its components. First step, right away, every time, we just want to break it up into the components, because that's what we're going to use to do our summation of forces. So then we have an x component would be T3 cosine 60, and the y component is T3 sine 60. And it's just chapter 1 stuff, right? So here's our 2 free body diagrams, and now we can use this to solve the problem. So if you look through the book, there's a couple ways we can solve it. We can either, if we're just given the weight in terms of W, we can solve everything in terms of W, right? So T1 would equal W, right? Tension 1 is equal to the weight. The direction suggests they're opposite signs, so the magnitude is exactly the same. So tension 1 is equal to the weight. And then we can find out tension 2. And I encourage you guys to look through the rest of this example from the study area on Mastering Physics. I'll just put the answer out here. So we know that in the y component, we can do a summation of forces in the y direction. Then I know that T3 sine 60 has to equal T1, right? So T3 sine 60 equals T1, but T1 equals the weight, right? So T3 sine 60 is equal to the weight as well. So I can find T3, just weight divided by sine 60. And then I can say, well, once I find T3, then I can find this component right here, right? So T3 cosine 60 would be this one, and T2 must be equal to T3 cosine 60, right? So we can write all these, and you'll see that in an example. We can just write a bunch of equations. We can write really using our summation of forces in the x and y. We'll write one equation here. It's really T1 minus W equals 0. It's our summation of forces in the y. And we have one here, T3 sine 60 minus T1 is also equal to 0. And T2, or actually this is my positive x direction, so T3 cosine 60 minus T2 is also equal to 0. And so we have 3 equations and 3 unknowns, right? Or at least we can solve everything in terms of W anyway. So if we assume, as your book does, you assume that the weight was 2,200 newtons, then we can get nice forces for all these tensions here. So we get T2, T3 as shown here below. So what's the biggest force? It would be a tension 3 here, right? Does it make sense? Does that make sense that the tension 3 is the largest one? Let's go back and look at the picture here. Is tension 3. Well, tension 1 has to support the entire weight of the object, of the engine, right? So, okay, it seems you might think, oh, that one should be the biggest one since it's supporting all the weight. But don't forget that tension 2 is holding against the wall, then tension 3 is not only lifting it, because tension 2 isn't lifting it all. Tension 3 is not only lifting it, but it's also pulling it out to the side. So it's all the tension, it's all the weight plus whatever tension is here. So it does make sense that T3 is the most. Okay, let's do another example here. So this is a fun little problem. Lifting granite and dumping dirt. So we have here, we're working as miners or something like that, and we have this granite that we're pulling out of a quarry, and we're bringing it out at a ramp inclined at 15 degrees above the horizontal. And when we take the rocks out, we need to obviously fill it back in with something so we don't have such a huge hole. So they say, hey, you have to fill it in with dirt as well. So all the granite you take out, you also need to put in some dirt. So we have here, our boss asked us to devise some sort of a scheme that allows us to use this dirt that we have to put in there, use that to help us to lift the granite out so we can save energy or save manpower or however we're going to take it out. So basically, we need to use this dirt right here to pull up this granite right here. That's the idea. So if we stick with our usual coordinate system, it might be a little bit difficult to interpret. So let's look at this a little bit differently than we looked at the last problem. So the thing is that if we have a coordinate system that goes, our vertical is like this is our positive y, and then our positive x is this direction, then the motion here is sort of a little bit tedious to compute, right? It's not incredibly straightforward. Our summation of forces in the x and y direction. Well, as it moves along here, it's moved both x and y. So it's a little bit more difficult to look at. So instead of trying to kind of take the motion and figure out how it's moving x and y as it moves along here, what we can do instead is just reorient our axes, which effectively does the same exact thing. So before we do this, it's going to be much easier to reorient them so that that's parallel, so it's parallel here, and then perpendicular to the incline. So that way we can just say, well, if I have a perpendicular, if my y direction is perpendicular to incline, what is my motion in the y direction? What is my acceleration in the y direction? Well, this cart is not accelerating into or out of the plane at all whatsoever. So I can have a summation of forces in the y direction will be equal to 0. So that's why it's convenient to tilt our axes a little bit, so that just makes one of those equations much easier to deal with. And then we'll have summation of forces in the x direction, or whatever, the acceleration or whatever conditions we have going on here in the parallel, right? So in order to do this, we're going to need to break the weight into its parallel and perpendicular components, right? Because weight always acts straight down, right? And then this is something that you guys all are very familiar with after kind of the first exam and the first study guide. Everybody should at least know the results of breaking the weight into its the weight here into its parallel and perpendicular components, which we'll see on this next slide here. Okay, so let's say that we have a object sitting right here, and it's sitting on a plane that is inclined in an angle of theta. Okay, this object has a weight. It has a mass, so it has a weight, right? Its weight is mass times gravity. So, and there it is, right? Mass always, or gravity always acts down, right? Because that's the acceleration due to gravity, right? The direction of acceleration due to gravity is always straight down. So what I want to do is I want to break into a perpendicular component, and I want to break it into a parallel component, which actually we'll just say is a direction t. We have some pull here, tension. That's in our parallel component, right? And we have our perpendicular component here. So in order to do this, first note that if we have a triangle here, right? We have this little triangle we can make here. We can make a right triangle out of it. So then this part here would be 90 degrees, and then this would be 90 minus theta, right? So, and this is 90 minus theta, and this is a right angle here, right? This is a right angle here. Then what does this angle have to be? So this angle and this angle would add up to 90, and if this one is 90 minus theta, then this one must be theta. Right? So that angle right there is theta. So what we're trying to do, we're actually just going to try to get another triangle here that we solve for perpendicular and parallel components. Because the parallel component would be like this, right? This would be the direction of the parallel component. And the magnitudes are not drawn to scale here. If we had the proper magnitudes, I didn't put the time into drawing them to scale, but this would come down to here, then this would look exactly like this, and this one would come down here. But this is just a line that is in the parallel direction. So we know that, so this would be the force in the parallel direction, or actually the component of the weight in the parallel direction, right? And we also know that this is a right angle here, right? So there's theta, that's a right angle. This would be 90 minus theta if we want to solve that. So let me just put this in. So now I've drawn the parallel component, I've drawn the perpendicular component, and like I said, if I had the magnitudes scaled off properly, this would just come to here, and then this one would be here, and then mg would come down like that. Or maybe more accurately, this would have been down here, goes up to there, etc. But I didn't draw them that way. So if I take this, I have my parallel component and I have my perpendicular component, and I just take this triangle right here and I just rotate it, basically, and it's the same triangle that's drawn right here. This is mg, this is mg parallel, this is mg perpendicular, right? So then I can find them. The perpendicular would simply be this part right here would be mg cosine theta, and this part right here would be mg sine theta. So this direction, this green arrow, is mg sine theta, the weight times the sine, and the perpendicular would be mg cosine theta, or the weight times the cosine theta. For equilibrium conditions, special case, for equilibrium conditions, if I have some tension here and I have some weight down like that, then the tension has to equal the weight, right? So the tension would have to be equal to mg sine theta, right? The tension here would be equal to the parallel component of the weight, which is, this is mg sine theta, so the tension is equal to that for equilibrium conditions. Also, that's equilibrium conditions in the parallel direction. What about equilibrium conditions in the perpendicular direction? Well, this is the component of weight perpendicular. then I have a component of the weight that would be normal as well, right? Coming out opposite direction. That's what keeps it from falling into the surface. So the normal, if I have my axes like this and like this, then I have a summation of forces along here has to be equal to 0. So my normal force would have to be equal to my perpendicular component of the weight, right? Or I would say that the normal force is equal to mg cosine theta. Okay, really important for inclined planes. You guys remember these, right? Or you could say, mg sine of 90 minus theta, but it's easiest, when theta is given as the angle of inclination, then it's easiest to say, okay, we have tension as mg sine theta for equilibrium conditions. Then the tension would be equal to mg sine theta, and then for equilibrium conditions and the perpendicular axis, then the normal force is equal to mg cosine theta. So now let's use this for the problem. So now that we know how to break the forces into their parallel, the weight into its parallel and perpendicular components, let's free body diagram the cart as one free body diagram with our new coordinate systems, and we'll also free body the bucket, and we'll free body diagram these independently. We'll free body diagram them separately, analyze them independently, and then we'll connect them with this tension that goes between the two, right? The tension in here is going to be the same as the tension in here, right? So when we do this, is reorienting our coordinate system for the cart going to affect the analysis of our bucket? So now I have, we flip the axes, so we have perpendicular and parallel here. Does that mean we have an axis like this and like this over here now? No, it doesn't. We can actually still analyze this system with a vertical and a horizontal axis like this. So I can analyze the bucket here with one coordinate system and analyze the cart with a different coordinate system. Because the tension, regardless of how I analyze it, the tension is going to be the tension, right? So here the tension acts vertically, so I'd probably set it up, so that my vertical is straight up and down, and then the tension acts at this 15-degree angle here, so that's why we change our axes here. And there's a smiley face for you. So, like I was saying from the last slide, we can break the problem into two parts or more parts. We could break it into 5, 6, 10, 15, 100 different parts, and analyze every one of them differently with different coordinate systems for every one of them. But we'll break this into its two parts here. So we have the bucket and we have the cart, right? And we'll give them each a coordinate system, right? This one, the bucket, will stick with a standard, to the right and up, horizontal and vertical, and then the cart will have the one that we discussed previously with the parallel and perpendicular, and breaking the weight into those components as well. So then, similar to the problem that we had with the engine, we want to find out what the weight of bucket 2 is in terms of weight of bucket 1, how the weights of the two compare. So the weight of the bucket versus the weight of the cart, how their weights compare. And we can do this. We could start by solving this one, but nothing is really given in terms of W2 here. So maybe we'll start with this one here first, because this one I can solve very simply. I know that it's just moving in the vertical direction. There is no horizontal direction. So let me start with this free body diagram. So if I free body diagram the bucket here, I have to ask myself, again, you have to ask, what is going on physically? And the problem said that we're trying to figure out a way to move the cart up the ramp. We're trying to move this cart up the ramp at a constant velocity, right? So the constant velocity means that there's no change in velocity, right? So it means that the acceleration is equal to 0. So if the acceleration is equal to 0, the sum of forces is also equal to 0. So this is in equilibrium. It may be moving, but it's still in equilibrium. It's not accelerating, right? So we can say that summation of forces in the y direction gives us the tension is equal to the weight of the bucket, W2 is what we're calling it. So that's one. That gives us one equation there. And then we free body diagram the cart here, and we call that W1. And then so we just draw that dot here. We have some tension that will act off in the x direction since we've oriented our axes to be parallel. So the x direction is parallel and the y direction is perpendicular. Then the tension acts in x, and also the parallel component of the weight would act in x, right? And it would act back the other direction. It would act back this way. And that one we said was mg sine theta, right? So that's W1 is mg, so that's W1 sine of 15. And then the perpendicular component of it would be mg cosine theta, so that's W1 cosine 15. Or so the normal force would be out at here, which is equal to W1 cosine 15. This comes from summation of forces in the now x direction and the y direction. This disappears when I break it into its components, right? So if I do summation of forces in the y direction, I have the normal is equal to the perpendicular component of the weight. So the normal force is equal to weight times cosine of 15, and the tension is equal to the weight times the sine of 15. Again, go through the example that you see in Mastering Physics in the study area for the work. I didn't write out any of it in this video, but we end up with the result of the weight of the bucket here in terms of the weight of the bucket here. We can solve for everything else. So we end up with W2, weight of bucket of the bucket is equal to the weight of the cart times the sine of 15, the angle of inclination, 15. So we finished that. It's always good to go back and kind of think about the problem a little bit. In this problem, we were asked to move a cart up a ramp at constant velocity. Which, okay, that's fine, but in reality, how we can't just move something at constant velocity. It must have started at 0, right? This cart is going to start out at 0 at some point and then need to go up here. And then when it gets here, it actually probably needs to go back down. I don't think the cart's going to come up here and then fly off, right? So we actually need to come up and then go down. So we probably do that by starting and stopping our flow of dirt in here. But how will we think about this? We'll run through this a little bit in class. But how could we start the cart moving? We'll take care of the fact that it's stopping and then rolling back down. We'll just start and stop the dirt. But we need to accelerate it somehow. So think about that, because this isn't a very practical solution. We need to accelerate it. Also part of this slide right here, I forgot. This is for constant velocity. Our solution was for constant velocity. So what's equal to 0 in constant velocity? We did this on the previous slide, but you guys should all say acceleration is equal to 0. Okay. Yeah, and think about how we can accelerate that cart for class. We can also use Newton's laws, Newton's second law, to find acceleration as well, right? So instead of equilibrium conditions in which summation of forces equals 0 because acceleration was 0, we can also have some non-equilibrium conditions, dynamic conditions, in which there is some acceleration, right? So in which case we would need to write Newton's second law as summation of forces is equal to mass times acceleration, right? Or the net force is equal to mass times acceleration. Or, in component form, we have summation of forces in the x direction is equal to your mass times acceleration in the x direction. And same thing for the y direction, summation of forces will equal mass times the y component of acceleration, right? And the same thing, if we had a z direction, we could also say summation of forces in the z direction would be equal to the mass times whatever the resulting acceleration is in the z direction, right? So same thing that we had a minute ago, except acceleration is not going to be equal to 0 in this case. So a quick little example, and again, work this out, and then look at the video example in Mastering Physics. But kind of an interesting little thing here. Let's say you're driving along in a car, and you decide not to pay attention to the road for whatever reason, and instead you look up here, and you have a protractor that tells you an angle, and you can measure angles off the protractor, obviously, right? And you hang a key or something with a certain mass. You'll need to know the mass. But you have a certain mass here, and it swings back when you accelerate, right? And you guys have probably all noticed this happening, right? You accelerate in your car and things swing back a little bit, right? It's sort of we'll break it apart here. You guys will see what it's from. But let's say we have the key. It kind of sort of swings back, and then it starts moving forward, right? So if I were to take this and I break and I just free body diagram this key, so I'll free body diagram this key right here, then I have a weight acting on it, right? And I have some tension in the string acting on it like this. So here's my key right here, and then I have some weight acting down right here, and then I have some tension up like this. Well, again, we're gonna, first step we pretty much always do is to break everything into their components, right? So change coordinate system if we need to. If not, just go ahead and break into the components. So let me say the weight is already vertical. So let me break the tension into a vertical and horizontal components, into our y and x. Now you have to be careful here. This angle beta would be measured off the vertical instead of off the horizontal, right? So it's actually this angle beta here. If I were to continue this line up, and then my angle through there, then this would be the angle beta right here. So this is beta, and so now it actually makes my x component the tension times the sine of beta. X component isn't t cosine anymore, it would be t sine because beta is measured off the vertical, and then the y component will be t cosine. Or you can always, if you prefer, you can say this is 90 minus beta right here, and then it'll be cosine, t cosine 90 minus beta, and this will be t sine 90 minus beta. Works out the same thing, works out the same way. So what happens is that we have equilibrium in the vertical, right? Because we know once the key is there, and this is stationary, you say, okay, it's swung back and now it's just hitting right here, right? And it's stationary, it's not doing anything in the vertical direction, okay? And so if it's not moving vertically, that must mean that t cosine beta is equal to mg, right? So if we know g, 9.8 meters per second squared, if we know the mass, and we measured beta, we can find the tension, right? So we can find the tension in this string. And now we also know that the x component, the horizontal component, is t sine beta. Well, if I know the tension and I know beta, I can find the magnitude of that force in the x direction, right? This is t sine beta, and there is no other force in the x direction. I know what's going on. This may not be moving relative to us, but in reality, the car is accelerating forward, and the protractor is accelerating forward, and the key that's attached to the protractor is accelerating forward as well, right? Everything's actually accelerating forward. So the summation of forces in the x direction here will equal mass times the acceleration. So t sine beta is equal to mass times the acceleration of the car. So this is sort of how we put Newton's laws into effect for things actually accelerating, right? Like I said though, finish up this example in the Mastering Physics section. We'll do many more of them in class. Okay, so we need to also, in this chapter, look at friction a little bit. So if we go back and look at some of the problems from chapters 2, 3, 4, we often said that everything was frictionless, because it was a simplifying assumption quite a bit. So now we want to take out that assumption and make it a little bit more realistic. So problems that we used to consider to be ideal are going to be more realistic now, right? We need to be able to find frictional forces given kind of the mass of it, or what the weight of it, and the normal force, and also the how the object interacts with the surface that it's sitting on. So in reality, we have, you have a block sitting here, right? And maybe you have a push or a pull or some sort of force and trying to move it to the side. And then you have a mass of it, and naturally that mass is accelerated due to gravity, because and so it has a weight, right? So mass times gravity is our weight. So we have these here, and if we also have no acceleration in the y direction, right? So we must have something to counteract that, and that's a normal force, right? So we've dealt with that one already. But there's also always a force which slows something down. This is why, Newton's first law says that anything will stay in motion in a straight line until it's acted on by something to change it, acted on by a force to change, right? So if I push on something that slides along the ground, then it has, if it comes to a stop, it's because there was something acting on it, right? And that is friction. So we have this other frictional component that's always resisting motion, and it doesn't necessarily have to be moving to resist motion. It just resists the kind of possibility of motion. So even if this block isn't moving, if I push on it in this direction, friction will still push back. It'll still try to resist kind of the starting of motion. But even after it gets going, friction will still slow it down. And there's actually a couple of different coefficients, we'll call them coefficients for friction, in those two scenarios, which we'll get into a little bit more. But really we have normal force and the frictional component are essentially two components of one force right here, which we just call the contact force. And this is the force, the contact with the block with the surface it's sitting on. Okay, but where does friction come from? Is the question here. So just to talk about it a little bit more. So you have that same block from the previous slide sitting on the floor here, and if you look at it very closely, this block is not perfect, neither is the floor. And there's probably, there's dirt and all kinds of other stuff in there, right? And so you have these little bumps, right? And so you kind of have two options. If this block is going to move to the right, then it either needs to interact with these bumps by breaking off either part of the floor or breaking off part of the block, or this block would physically need to, when it sits down in this little crevice here, it'd have to pick up in order to get that little divot over that, right? So either the block has to be lifted, you need to go against gravity to lift it, or I need to actually break the material. One of the two, but that's the only way it's going to be able to move forward, right? Much more likely it's lifted than breaking, but it depends on the material. So this is effectively where we get friction from. The coefficient of friction tells us how much force it will take in order to overcome this. You can imagine that if I had like sandpaper and something very, very gritty, and I put something else on top of it like rubber, which can actually fit well in these little crevices, then it'd have a very high coefficient, right? Or it'd be very hard to move. So the harder it is, the more resistant to motion, I should say, then the larger the coefficient of friction. So if we have a coefficient of friction of like 0.01, it'd be very easy to move. If we have a coefficient of friction of 1, then it's much harder to move, right? Some ways that you can reduce friction is, think about this for a second. Friction is essentially this interaction of these little bumps in here. So if I wanted to reduce friction, we talked about this in chapter 4 a little bit, I could put some sort of lubricant in here, right? I could put some sort of an oil or something like that, a film. This is what your motor oil does, is it lubricates it so that it can slide easier. Or like the air hockey table, you could pump a bed of air in between here, and so this would glide on air, so that it doesn't sit all the way down, and this can just move right over the top, right? Or even just water. I can just put water in between there, and it'll still give a little bit of a film for this to sit on, so that it can move easier, right? So that's some ways we can kind of reduce our friction coefficients. But let me talk about this difference between the getting it started and having it already going. Because if I put air in between here, you can see that if it's moving, then actually it'll kind of get more air under there, right? If it sits still, then it just sort of pushes all the air out. But once it starts moving, it gets a little bit of air trapped underneath it, and it moves much easier. Try this actually. Get a piece of paper and put it on a desk in front of you, and then blow on it so that you get a little bit of air underneath. First, it takes a second to get that air underneath, and it doesn't really start moving until finally it gets the air underneath, and then it moves very easily, right? So try that experiment. You can try it right now. Pause this, and then just get a piece of paper and blow it. Blow kind of off to the side a little bit so some air gets underneath, and you'll see that once you get the air underneath, it moves much easier. Right? So once it's moving, the coefficient of friction gets reduced quite a bit. Let's take a look at a graph of kind of what I was just saying here. So forces from static friction increase as the force increases, while forces from kinetic friction are relatively constant. And that's up until a certain point, the static friction increases, and then it becomes kinetic. So what's going on here is that you push on, this is pulling, I guess. If you don't pull on a box, so this is at point A right here, okay? Or if I don't pull on it, then I'm not trying to impart any motion on it, right? So I'm not trying to cause motion, so nothing is trying to kind of reduce motion. Nothing's trying to stop it either, right? So if I'm not trying to cause motion, then there is no friction trying to stop it. So the frictional force would be zero at that point, right? The frictional force is zero, right when well, if I'm not doing anything to it. Now, if I apply a little bit of tension, but not enough to get it to start moving, then the reason it's not moving is because there was a static friction force that opposed my motion, right? And it was the static friction force is strong enough so that it entirely opposes my tension, and it doesn't go anywhere. So right here, still no motion, right? The tension is here, the static friction is back, and it didn't cause any motion. So here I have the coefficient of friction, and I don't know if I gave this equation yet, but if I go back a couple slides, you can see that the normal force, how heavy something is, would dictate how easily it could slide across the ground, right? Because it was how much you needed to kind of lift it in order to get across those bumps. So the static friction is related, and as well as the kinetic friction, they're both related to the normal force. So in this case here, the static friction, Fs, force of static friction, is less than mu s. We call this the coefficient of static friction times the normal force. This is actually kind of the maximum frictional force that you can have. What mu s, the coefficient of static friction, times the normal force. So the higher the coefficient of friction, the higher the force can be, and also the higher the normal force, the higher the frictional force can be. So in this case B, we have some tension and we have frictional force, and the tension isn't big enough to go over the maximum static friction force. We have a maximum allowed, right? That's when the maximum static friction would be when mu s times the normal force equal the static friction force, which actually is what happens and part C right here. If I apply more force, it's going to be on the verge of moving. Right before something starts moving, that's when the force of static friction is equal to the coefficient of friction times the normal force. This is the one we'll focus on mostly because we'll be concerned with when it's about to move, right? Maybe sometimes I'll give you a force and I'll say, well, is it going to move or not? If I push on, I have a 500 Newton block and I push on it with 10 Newtons, is it going to move, right? And you would figure out the normal force, which would happen to be 500 Newtons, and I would give you a coefficient of static friction. You would figure out what that is and say, all right, that's the point it would start moving. Now, if that's less than my 10 Newtons I'm pushing on it with, then by all means it'll move. If this maximum frictional force is more, then it won't move. Okay. So in part C is what we have right here. The tension is applied, and that tension is equal to the frictional, the static friction force, and which is equal to the coefficient of static friction times the normal force. Okay, so that's what happens right here. And then once it gets moving, then we start getting some air kind of trapped under the bumps there, and the coefficient of friction becomes less, right? So once it starts moving, it sort of keeps moving. I can apply some force, and if for some reason it just starts moving, if I keep applying that force, it keeps accelerating, right? I can actually sort of slow it down a little bit after I've got it moving, or reduce my force on it. So that's because of the air is getting trapped underneath. So we call this is the kinetic friction force, right? So it's the same equation for kinetic friction, meaning moving friction, static not moving, kinetic moving, and this is simply a friction or a coefficient of kinetic friction times the normal force. So it's the same equation, it's just a different coefficient. Each material has its own coefficient as well. So I apply this tension here, and it's already in motion, and it overcomes the kinetic friction force, and it keeps moving. Okay. So this is, if it's not moving yet, we have the static friction force. If nothing's moving, then the static friction force is less than mu s times the normal force, the coefficient of static friction times the normal force. At the edge, when it's about to start moving, then the Fs, the static friction force, is equal to the coefficient of static friction times the normal force. So Fs equals mu s n. So always the static friction force is either less than or equal to mu s times the normal force, right? And then the kinetic force of kinetic friction is equal to mu k times the normal force. Once it's moving, that's what the force is. It's mu k and the coefficient of kinetic friction times the normal force. Once it's moving, that's a constant force. It doesn't really matter it does matter how fast it's moving, but not a whole lot. Well, enough to say in this class we'll say it's constant. So the coefficient of static friction is always greater than the coefficient of kinetic friction. That's because of, that air you get trapped in between there. So it'll always take more work to get it moving than it does to keep it moving. Okay, which is exactly what, or I shouldn't say more work, but more force. That's exactly what this line shows. I have to put, it has a greater frictional force here when it's static, and then you break through that, and then it's less of a frictional force. And just to put some things into perspective, I just pulled a table off of Wikipedia real quick, just to see what some coefficients of static friction are. Then we have, and it depends on both the materials, right? Because you have two materials interacting. So if you have like aluminum sitting on top of steel and it's dry and clean, then it's, coefficient of static friction is 0.61. If I have some smoother stuff, I like brass and steel. Brass is a little bit smoother than aluminum, so that coefficient of static friction is 0.51. If I had, things like Teflon tape over here, So I have like steel on Teflon or Teflon on Teflon, then that coefficient of static friction is 0.04. So just to put some things in perspective, if I had like 1,000 newtons of a normal force, so something that weighs 1,000 newtons, I would have if it's sitting on a horizontal plane, I'd have a normal force of 1,000 newtons. Then I would multiply that 1,000 newtons times 0.04, and I would get my force of static friction, which is 40 newtons, right? 0.04 times 1,000 is just 40 newtons. So if I have 1,000 Newton piece of steel sitting on Teflon, I would only need to apply 40 newtons of force in order to get it moving. So pretty good. So the more we can reduce the coefficient of static friction, the better off we are. And how do we reduce that? Well, we have some stuff over here that's lubricated, right? If I lubricate the steel on Teflon, it actually doesn't change it a whole lot. It doesn't have a huge difference in there. But if I have steel on steel, it's 0.8 when it's dry and clean, but if I lubricate it, it jumps down to 0.16. So this is essentially 80% of the normal force. This reduces it down to 16% of the normal force. So it's pretty good. Another big one here, concrete on rubber. So when you're driving, right, coefficient of static friction is 1 for concrete on rubber, or rubber on concrete is more realistic. It's our car tires on the road, right? So coefficient of static friction is 1, right? So it takes the same amount of force as the weight of our car in order to start sliding. But what happens when it rains? Well, it gets lubricated with the rain, and so the coefficient of static friction reduces down from 100% to 30%, down to 0.3. So now it only would take less than a third of the weight of your car in order to slide it off. That's why it's, you slide more when it's wet out. And then if you put some oil on the roadway as well, then it reduces even more. Okay. Okay, here's a good example applying friction to this problem. And I'm not going to run through the whole thing just to save time and size of the video, but make sure that you guys either go through the example in the book or watch the example video on Mastering Physics. But let's say we're going to pull this exercise equipment that's in this box, and we're going to try to pull it horizontally for one case, and then we're going to try to pull it up in an angle for the other case. Now, if this were frictionless, we would surely say, and we want to find out which one's easier, right? And if it were frictionless, we would certainly say, well, I want to put all of my force horizontally, right? I don't want to put some of my force into lifting it, because that doesn't make any sense. All I want to do is move it horizontally, because this would be, this is our tension here. Then I have the x component would be tension cosine of 30, and the y component would be tension sine 30, right? And so if it were frictionless, we would say, well, pulling it horizontally is best. But now that we've introduced friction, it changes the game a little bit, right? Because friction depends on, it's some coefficient of friction, which they actually give us. The coefficient of kinetic friction is 0.4. And so the frictional force that's resisting motion here is 0.4 times the normal force. Well, the thing is that the weight is 500 newtons, right? So if I pull horizontally, the only thing stopping it from falling is the normal force, right? The pushing back up. So I have to have a normal force of 500 newtons. So then my frictional force would be 0.4 times the 500 newtons, right? So it would be, 200 newtons of frictional resistance. That would be horizontally, right? Now, if I put part of my force into lifting it, so I pull upwards, then I actually I'm giving it a y component of velocity, right? So effectively what that does is it reduces the normal force. Let's say that we pull, and you'll run through the example and and solve this. But let's say we end up pulling at, let's say our tension is 200 newtons. So we have 200 sine of 30 would be our y component. So that's 100 newtons. So we're effectively reducing the normal force by 100 newtons because we're lifting up 100 newtons. Then our normal force would be the weight minus that 100, it'll only be 400 newtons, right? So 400 newtons, and then we could say our frictional force would be 400 times 0.4, so it'd be 160 newtons. So we've reduced the frictional force there, right? Of course, we've reduced how much of our force goes horizontally, but we've also reduced friction. So we need to figure out, well, if we're going to pull an angle of 30 degrees, which one is going to be better? And we can find out the tension needed in either case, which is exactly the example in 5.10. But I wanted to run through you guys sort of the concept behind that one, and then try to do it, and then go through the example. It's the best way to learn that. And I think the results are on the next slide, so do that before going on. So you get down to the results, and you say if we pull horizontally, then our normal force is going to be equal to the weight, which is 500 newtons. And the tension we'll need to pull is 200 newtons in order to move it, in order to overcome friction. If we pull in an angle, our normal force ends up being 406 newtons, and our tension ends up being 188 newtons. So we actually don't need to pull as much if we pull at an angle. We can pull a little bit less because we reduced the normal force. So physics, yeah. So it can be a little bit easier to pull at a little bit of an angle, depending on your coefficient of friction, of course, right? If I increase friction more and more, I'd want to lift it more and more until the point where, you've probably done this in real life. Something is very hard, the coefficient of friction might be 2 or something. So it's twice as hard to push it as it is to lift it up. So maybe like cleats or something like that. And so it'd be much easier simply to lift it and carry it and move it over than it would be to push it, right? So depending on the frictional coefficients dictates how we move it. Okay, the last thing we need to go over here are the elastic forces. So like a spring or some other elastic material that exerts a force when it's stretched or it's compressed. Things that want to go back to the state they were in. If I pull on a spring and then I let go, the spring doesn't stay there. It actually pulls back, right? So it has a tendency to go back to the position it was in. And same thing if I take like an elastic band, rubber band. If I stretch out a rubber band, then I let go, then it contracts back to the shape it was in before, right? So that's any sort of elastic material that wants to kind of go back to the state it was in before and wants to go back to equilibrium follows this law, and it follows it pretty well. Not perfectly, but close enough to where we'll use it. But it's Hooke's law. So the force the spring exerts on the object, the force of the spring on the object is equal to negative kx, right? So where k is a spring constant and x is some displacement from equilibrium. So what does that negative sign mean, really? If this is the force the spring exerts on the object is equal to negative some spring constant, which is just measured quantity you have for every spring, and then times the displacement from equilibrium. So the negative, well, let's run through the pictures to figure out what that negative means. If I have a block here and x is equal to 0, then, and this spring is in equilibrium, it doesn't want to it's not being stretched out, it's not being compressed, it's in equilibrium, it's sitting there in its natural state, then there would be no force that the spring exerts on the object, right? They can just sit here together in equilibrium and be fine. Now, if I were to pull this out, if I were to pull this block out, then the spring is being stretched from its equilibrium position, right? And I've displaced it. I've displaced this x in the positive direction, right? I moved it You know, I had x equal to 0, now x is equal to 5 centimeters or something, right? So I gave it some positive displacement. And K is in, you know, like newtons per meter or something. So let's say I displace it 5 meters. When I go newtons per meter times meters, I'll get newtons, so I get a force, right? So the units of the spring constant are newtons per meter, or pounds per foot, or pounds per inch, or something like that. But it's always some force divided by distance. That way, when we multiply by distance, we'll get force. But anyway, so I displace it to the positive direction, but the force exerted by the spring on the object is opposite the displacement. So that's what this negative sign means. I displace it to the right, the spring tries to pull it back to the left. If I displace it twice as far to the right, the spring would try to pull it back twice as hard to the left, right? The magnitude of the spring force is proportional to the displacement. You can see it's directly proportional, right? It's just multiplied. Spring force is equal to negative kx. If I displace it the other direction, if I compress it here, then I've given the x a negative x, right? I've moved it in the negative x direction, so then the force of the spring would be negative k times negative x, so negative k times negative x, so we would have a positive spring constant, okay? Or not a positive spring constant, but a positive spring force. The spring constant is always positive. It's a scalar value. Has no direction. So that's Hooke's law. Just the force that a spring exerts on an object is equal to the spring constant times the displacement, and it's in the opposite direction of the displacement. And that's the best way to think of it. The force of the spring on an object is equal in magnitude to the spring constant times how far it's being displaced, and it's in the opposite direction of the displacement, essentially what it is. So the force the spring exerts is always opposite direction as the displacement. Which I think that does it for chapter 5, but I want to run through a bunch of the multiple choice questions. So let's do a few of those now. Okay, so this is multiple choice 5.2. I'll just do a bunch of even problems since you have the odds in the back of the book. But you slide an 800 Newton table across the kitchen floor by pushing with a force of 100 newtons. If the table moves at a constant speed, the friction force with the floor must be what? So we have some table that has some weight, and we're going to push it across the floor. We're going to with 100 newtons. And the key is here, and this is something to watch for in your questions and quizzes, tests, whatever, life. The table moves at a constant speed. Constant speed would mean that the speed is not changing, right? Which means that the speed is not changing, neither is velocity, and it is not accelerating. So if it's not accelerating, then it must be in equilibrium, right? So if it's in equilibrium, then the sum of forces also must be equal to 0. So if I'm pushing with 100 newtons, and I know that there's a frictional force resisting me, and I know that the sum of these forces is 0, then the friction force, which is resisting me, must be exactly equal to the force I'm pushing on it, because the speed is constant. Okay, multiple choice 5.4. You have these two carts here. One of them of 2,000 newtons, one of them at 500 newtons, and some force P pulling on the 500 newton cart, and some cable connected them, right? It says that the tension in the light horizontal rope connecting the wagons is what? So this is the light horizontal rope connecting the wagons, right? So, what does it have to be? So I pull on P, then this is really a matter of free body diagrams. Draw a couple free body diagrams, and let's consider if I were to put a free body diagram around the entire thing, then I apply some force here, and that equals this total mass, 2,500 newtons, and then times its, well, this isn't the mass, that's actually the weight of these, but I can figure out the mass by dividing by gravity, right? So I'll take the mass of these times whatever acceleration, that's what P is equal to, right? And now they have to be accelerating at the same speed, right? These are accelerating together, means that, let's say they're accelerating 1 meter per second squared. So this whole thing is accelerating at 1 meter per second squared. That means that this is accelerating at 1 meter per second squared, and so is this, right? So if I look at this one, if I just free body diagram this guy, then I have some force here which is causing only 2,000 newtons to accelerate at 1 meter per second squared. So P causes 2,500 newtons, 2,000 plus 500, 2,500 to accelerate at 1 meter per second squared. But this force, whatever this force in the horizontal rope, only makes 2,000 newtons accelerate at 1 meter per second squared. So it would have to be less of a force, right? This one has to be less. This P has to accelerate both of these, versus this one only has to accelerate this, right? So another way you could probably look at this is you could say, well, there's a P here, and then there's this one. This is pulling back, and this is pulling back at the same magnitude. This is pulling forward, right? And this one is both that's pulling forward and it's accelerating. So this one is greater than the tension here. So P has to be greater. So if I'm looking for the tension in the light horizontal rope, then it has to be less than P, because this is only accelerating 2,000 newtons. If I were to tack another one on here, if I were to have another weight back here, another rope and another cart, then I have this is the most, this is next, and this would be the least, right? Because this P we need to accelerate 1, 2, 3 carts. This one we need to accelerate 1, 2 carts. And then this one back here would only need to accelerate the 1 cart. And again, if I put another one on the end, then that's the lightest one, right? So it's always most likely that the frontmost one will break first, right? Okay. I think to save time, you guys should just pause these, read it, try to get an answer on your own, and then I'll just jump into the explanation for the rest of these. So if this crate is sliding up an inclined ramp, it's asking us which of these is most accurate. It slides up, stops, so it slides up here, then stops, and slides back down. Well, it says something about the acceleration, right? The acceleration going up the ramp is greater on the way up than going down. It's greater going down than on the way up, or it's the same in both directions. Well, the thing is when it's going up, then it's being accelerated downwards at G, right? Or some component, mg, G sine theta, right? So there's some component of gravity pulling it down, right? So there's that. And then you also have when it's moving up the ramp, if it's moving up like this, friction is resisting motion, right? So friction is also working down the ramp. So you have friction and gravity are both working in the same direction down the ramp. So that's a pretty big magnitude, right? The acceleration going up the ramp is greater than going down. Well, let's see. What is the acceleration going down the ramp? Well, going down the ramp from here to here, well, it's accelerating downwards due to gravity. So same as we had on the way up. But now when it's traveling down, then friction is actually working up the ramp, right? So the magnitudes of those accelerations are not added, they're subtracted. Gravity is working down, but then friction is working up. So it is actually greater on the way up than it is on the way down. So the answer is A. This is essentially just asking, what is tension? So I have, and we saw this from the previous slides, actually from chapter 4. We have a weight here, right? W. So weight W pulls here, right? It goes to the rope. It's the same everywhere, right? So I have a weight. Tension is equal to W here, and this is a weight, so tension is equal to W here. So I have a tension pulling back here of W and a tension pulling here of W. If you were to cut this out, this scale out, and so it were just continuous rope, what would you say the tension is there? Would you say that the point that the two come together, and this is not there, so let's say the rope is coming along here and I slice it right there. Would you say the tension is 2W because there was a W here and a W here? Or would you say the tension is just W? Or would you say it's 0? Hopefully you said that it would just be W, because this is just, it's the same tension everywhere, right? It's pulling here and it's pulling here. That's a tension force. Just the fact that I have a tension of W here and a tension of W here keeps it from moving, keeps the scale from moving to the side. If this were 0 here and if the left side was a tension of 0 and the right side was a tension of W, then I would have no tension in this cord other than the weight of this, and it would just accelerate to the right. So the fact that I have W on both sides keeps it in equilibrium, but the tension is just W. It's just the tension in this rope right here. So in problem 5.10, we have this 100 Newton ball here that is being suspended by these wires A and B. And it says, what can we tell about the tensions, right? And they're at the same angle theta, right? So we have this angle theta, both of them are coming down. Obviously, if it's the same angle theta, then this distance here is more, but don't let the distance confuse you too much. It's just this is just the distance that comes over here, and this is the distance that comes over here, but that just means that this rope is longer. It doesn't really have anything to do with the forces there. It's just that it's a longer distance here. It's a bigger triangle than this one, but they're similar triangles. So the question is, what can we conclude about the tensions, right? Well, what can we, conclude about this ball? It has a weight down, right? If I were to draw a free body diagram, it would have a weight down here, and it's not moving down. And so the y component of this weight, or the entire weight, must be taken care of by the y component of these two tensions, the tension in A and tension in B, right? Well, since these triangles are similar, that's theta. This, if I measure off the horizontal, that's theta. This is theta, and this is theta, right? So these are actually, the y component of this one would be A sine theta, and this one would be B sine theta, right? And now there is no x component other than the A and B, right? So if I have the x component B would go off this way, and it'd be B cosine theta, and this one would be A cosine theta here. So their x components have to balance out because this isn't moving. So if their x components balance out and they're both B cosine theta, A cosine theta, then A equals B. So we can say they are both equal, right? So it takes, well, A says they're equal, B says they're equal, C says they're equal, and D says they're equal. That doesn't eliminate any. So we know they're both equal because their x components balance out, because the thetas are the same. Well, the next thing is that what about their y components, right? This is, in order, I must have B sine theta plus A sine theta equals 100, right? Well, sine of theta, unless this is at 90 degrees, sine of theta is less than 1, right? So I'm going to lose some of my force from this when I'm taking the y component, right? So this is, if I need these two to add up to 100 newtons, these are both going to need to be greater than 50, right? Depending on the angle. If these were both 50, they would need to both be vertical in order to make up that 100 newtons. So depending on the angle, it will make these be stronger and stronger, or larger and larger tensions, right? They have to be more than 50 so that when I take the sine of theta, I'm left with 50 each. So the answer would be C. The tensions are equal, but they're greater than 50 newtons each. Okay, so this is the last multiple choice problem from chapter 5. And so we see we have a system here, some block and some pulley pulling on this another block right here, right? And so it's going to pull on it. It says there's no friction whatsoever between this block and the countertop, the tabletop. And then there is a frictional force between A and B, though. And it says that everything moves together, right? It doesn't actually say which direction it moves. It just says they move together. Well, there's no way that it's going to move to the left, right? These can't pull without some external force. These aren't going to pull it up. Our external force is gravity. So this is pulling down, so then this is pulling to the right. So this whole thing right here moves to the right. So what's true about the friction force on A? How is A moving? Well, this tension will pull B, and there's no friction here, so I don't need to worry about that. But the tension here will pull B, so B will start moving. And now if A is going to start moving as well, then there needs to be something to transfer that force, right? So if A is going to start moving to the right, then I must have a frictional force on the bottom here, because there's nothing else touching it. I must have a frictional force on the bottom to move to the right as well. So the friction force on A is that the thing that's true is that it acts to the right on A and must act in order to accelerate it to the right on A. And we'll do a bunch more chapter 5 problems in class.